So hello, good morning everyone. My name is Amir Aliabadi from the School of Engineering, University of Guelph, and I welcome you to the course on Theory and Applications of Turbulence. I will briefly go through the outline of the course, basically what we are going to do, the topics we're going to discover, deliverables, and then we'll begin chapter 1. So if you read the course description here, there's lots of books and courses already on the topic. I would consider this as a very fundamental course. I mean, we will go deep down the mathematics and physics. We do a bit of programming, but we are not going to complicate or overcomplicate the subject. For example, a lot of times we reduce the dimensionality of the problem. Like, let's say from 3D we go to 2D. 2D, we go to 1D, or from transient, we go to steady. Because the take is fundamental. Okay, but still there is a fair bit amount of math and programming involved, which hopefully you will enjoy. So let me read a few sentences of the course description. Theory and Applications of Turbulence is a graduate course designed for future scientists and engineers to develop the fundamental and applied knowledge needed to understand, analyze, and design turbulent processes. Lectures are going to be Tuesdays, Thursdays, 10 a.m. to 11:20 a.m. There is no final exam, which should make a lot of us happy. So here's my contact information. So if you need to come see me, here is my office phone number, email. We already announced the office hours on the board. The course has a textbook which I have developed myself, and it's freely available on the internet. It's called Theory and Applications of Turbulence, a fundamental approach for scientists and engineers. You can download it from my website. It's also on CourseLink. You can download, print it out, and use it. There are also recommended textbooks which you don't need to necessarily invest in or buy, but I highly encourage that. I mean, they add nicely to your personal library of engineering textbooks. The first one is Turbulent Flows by Pope, and that has an engineering take approach. I mean, so for people in the engineering world, let's say the Archimedes screw research, it's very relevant. The other one is by Stahl, An Introduction to Boundary Layer Meteorology. That has sort of a science take or approach or flavor, specifically atmospheric science. There's also the third book, Turbulence, An Introduction for Scientists and Engineers by Davidson. And that one fits all, basically. It's a very good book also. Please stay on top of the announcements and postings on CourseLink. All of the assignments, annotated lecture notes, everything will be posted in CourseLink. I also make frequent announcements, like how to do this and how to do that and what's coming up, so on. You are expected to provide a seminar toward the end of the course. So we call this a paper presentation seminar. In this seminar, you will present one of the recent journal papers in the field, which you've read and you feel like it's needed for your research or you're just interested in. You could actually present your own paper too, if it has been published. So we run this as a critical examination of literature in the journal. So you present it, people ask questions, and so on. We will finalize the paper selection, topic selection near the end of the course. So this seminar happens near the end, and you can talk with me what you want to present, and if I see it's appropriate. The computer labs, these are basically assignments, computer assignments. You can do it at home, but we just call them lab. So we are going to cover a lot of the fundamental and applied topics in turbulence in these computer assignments. The first half of the assignments, the first 7, are related to turbulence data, right? I'll give you a lot of measurements, which I have done as part of my research, and then you will analyze the data to understand turbulent properties of flows, right? So there's no modeling involved here. It's just crunching numbers, which is very useful, in my opinion, on the understanding of the topic. So the first 7 will cover those. And then the remaining 8 relate to modeling, in which case there's no field observations, but I ask you to develop a model of turbulence. And these models are really simple. For example, most of them are one-dimensional models. But you start from the bedrocks of the equations, you build the equations, you discretize them, and then you solve them numerically. Right? So that's the take here. And again, this should hopefully be useful to help you understand the topic better. Finally, there are 2 term tests, term test 1 and term test 2, where I will examine you on the topics. Basically, these are problems that you solve on your own time. Last year, we made it a take-home exam. People had half a day to do it, and it worked well. So this year, we made it the same. Okay. So the term tests add up to 30%, 15% each. The computer labs and assignments add up to 60%, each one's 4%. And the paper presentation is 10%. Okay. If I'm going to encourage you in anything, it's please stay on top of the computer labs and problem sets in the book. Right? Please do not postpone those, because quickly the material makes progress, and if you're not exploring those, at some point it may be impossible. Right? So week by week, try to do those assignments and solve problems, make progress, and then come see me if there are questions. So that is it about the course outline. So let me see if there are any questions. Is there any questions before we start chapter 1? Sounds good. So the first half of the lectures I'm giving you are related to fundamentals. So this I like to call the part 1 of the course, which take care of the fundamentals of the topic. So we are not going to do a lot of modeling here, although we are going to go dive deep down in the equations and see how they come about and how they're developed. But it's all fundamentals. In the second half of the course, and that will be after term test 1, we switch gears and we do a lot of exercises modeling. Okay? So as I go through the notes, I will just go through the notes page by page, and I always think an effective learning method is to write, right? I don't want you to write your own notes. I mean, you're welcome if you want to. But one thing I encourage you is to scribble information around the lecture notes. Like underline a keyword, write a piece of equation on the top right corner, write a schematic on the left bottom corner, and things like that, right? So the more you sort of annotate the lecture notes, the more I think you would exercise the learning experience. And that's what I'm going to do. I'm going to put a lot of information on the notes and then later share them on Coursely with you. Even if you don't want to write, just want to listen, define it. So in fluid dynamics, turbulent flow is a flow regime characterized by property changes. It's a very nice definition that fits all, basically. Can someone suggest what is a property? I mean, what is property in general of a system? Let's say the air in this room. What's one of the properties of air in this room?
Volume, mass, temperature,
Temperature, density, humidity, velocity, pressure, right? These are properties. So if this flow or airflow in this room is in a way that these properties change chaotically and I can't really well predict, then the flow is turbulent. And I can assure you, if you bring a very sensitive anemometer, the device that measures airspeed or temperature or humidity, pressure, if you put this very sensitive sensor here and you record its measurement, it's going to be noisy. If you look at the measurement, it's going to be lots of fluctuations. And that's the nature of turbulent flows. What's interesting is it is ubiquitous in everyday life. From airflow in cities and buildings to water flow in rivers and oceans and Archimedes screws. Even voice generation, you know, when you talk, the air goes through your vocal tract. It goes around your tongue and teeth. It's turbulent flow that allows me to speak. Right? All this noise that is turbulence. If turbulence didn't exist, you did not hear me. Basically, it's really spectacular. You can visualize it. Let's say the cigarette plume that all of us look at. If you look at motion of smoke, you cannot predict what the smoke is going to do in the next second or two. It just develops very chaotically. It's another example. It is difficult to understand, measure, and model or simulate. And it's funny, it's one of these problems that's one of the oldest problems in classical physics. I mean, this problem is as old as we've been doing engineering. Right? From the day we built the first water system, right? This problem existed until today. And it's the unsolved problem of the physics. You cannot solve it exactly. It is complicated, but at a fundamental level, it's easy to understand it. You actually know what happens. You can't just predict it. Okay? So you know the physics, the principles behind these types of flows, which makes it interesting. If you want to define it further, what causes turbulence? Turbulence, at the fundamental level, is caused by growth of instabilities in fluid motion. Instability. What is then instability? Well, instability is a process where a system was stable before, it was ordered, it was not chaotic, and then you triggered some change in the system. And then that change grew and made the whole system unstable. Okay? So it's a process. And the concept of instability is parallel to the concept of perturbation. Right? Systems are perturbed by boundary conditions or what happens to them, right? They evolve. So if you perturb a system and it becomes unstable, it's a turbulent system. And I find this analogy very useful. For example, if I have a trough and I place a ball here, okay, so the ball is here, it has some mass. This trough is sitting in a way that gravitational acceleration is pulling down, and I have a ball here. If I move this ball, if I perturb this ball, if I kick this ball to one side, what's going to happen? The ball will come back to the starting point. Maybe it oscillates a couple times. There's friction, but at the end it will stay there. So this system is a stable system. You can have more complicated situations. Let's say I have this situation. What happens if I push this ball to the right? If I push this ball to the right, it may actually come back if I perturb it very little bit. So I just push it a little bit, it'll come back down to where it was. But if I push it too hard, then it's going to go over the local maximum of the curve. Finally, it'll drop down. So it depends what happens. It depends on how far I perturb it. These type of systems we call, do you know what we call them? We call them conditionally stable. We call them conditionally stable because it depends on how far you push it. But there are other systems that are unstable 100%, right? If you put this ball on the top of the heel, then whatever bit of perturbation it experiences, it is going to fall down. This is for sure an unstable situation. So when we say turbulent flows are flows that are unstable, some sort of instability grows in them, right? These flows experience perturbation. There's a boundary condition that's moving. There's something that causes the flow to change, and that always it's in the direction of growing instability. Okay. The first person who studied this systematically and documented it, I'm sure people have done it before, but the first person who studied this systematically and published his work was Reynolds in the later half of the 19th century. And Reynolds designed a very clever experiment where we had water flow in a channel. He changed the velocity of flow going down the channel, and he injected some sort of a colored dye. At very low speed, he observed this colored dye does not disperse and mix really well because the flow is stable. Any sort of perturbation damps out and remains as a stream of color. But when he increased the velocity, he found that the mixing goes up and the instability grows. Okay, I'm going to show a picture of that for you in a moment. But he came up with this non-dimensional number, which we call the Reynolds number. And the Reynolds number characterizes the relative importance of inertial to viscous forces in a flow. If you have any flow, you can characterize the velocity in this flow by some number. We call that U, a fancy U. The size of the flow we can also characterize by L. And nu here is just the kinematic viscosity of the fluid. Okay? Let's say the characteristic size of this room, if I want to analyze flow in this room, what's the characteristic size or length scale of this room? If you just want to give me a number. Very approximate. Height, right? Like 4 meters or 3 meters. You could also give me the side length, or that side length, or even the diagonal length. Doesn't matter, right? It's some number that very well represents the size of this room. What about the characteristic velocity of air in this room? What is a typical air velocity in a building? Very approximate. I'll give you two options. 0.1 meter per second, 1 meter per second, and 10 meters per second. 1, right? I mean, typically, by and large, it's in the order of 1 meters per second. You're not going to get 10 or 20 meters per second of air in buildings. And it's not always so calm that it's almost close to 0.1 or a few centimeters per second either. It's usually in the order of 1. If you multiply the two numbers, velocity times length divided by kinematic viscosity, you get a number. And this number signifies how chaotic your flow is going to be. If this number, Reynolds number, is less than 1,000, the flow is said to be laminar. If it's in the whereabouts of 1,000 to 4,000, the flow is transitional. And if it's more than 4,000, the flow is turbulent. So this number, the relative magnitude of it, signifies if the flow is turbulent or how much tendency there is to instability growth and turbulence. It's very approximate. I mean, you should never compare two systems, one with Reynolds number of 900, one with Reynolds number of 950. You see what I'm saying? This is a very approximate type of calculation. You always compare like a factor of 2 or 3 or an order of magnitude change in Reynolds number. I can put a picture to the Reynolds experiment through. So let me do that. So Reynolds experiment, there is the characteristic velocity. U, characteristic length, so what he had a sort of a pipe or a channel. Water was flowing down this channel, let's say with velocity v. And then he injected a dye here. So that was a color dye. At low velocities, it's interesting. Oh, by the way, the diameter of the channel was d, or the height of water flow in that channel. He observed that at low velocities, this dye remains as sort of a centered stream of color at the center of the dye. Even if there were perturbations, they were damped, right? So in laminar flow, perturbations are damped. Perturbations are damped. Or, alternatively, instabilities do not grow. Right? And for this problem, well, the velocity, characteristic velocity u, you can take that as velocity of water in this pipe or channel. And L, characteristic length, you can take the diameter. Okay? So this is what happens under laminar conditions. So this thing happens when Reynolds number is less than, say, about 1,000. But on the other hand, if Reynolds number is more than 4,000, this color dye, if there is a perturbation, it is going to grow to the level that at some distance downstream there is full mixing of the dye. So this is turbulent flow. Instabilities grow. Instabilities grow. Very simple and ingenious experiment. In fact, the setup he made was developed at the University of Manchester, the UK. And if you go there, if you go to Manchester, go to the university, this setup is there, right? So it's a sort of piece of history of turbulent flows research. It's still there. You can watch it and look at it and get impressed. So it's fun. So what we talked about, the cigarette plume, there's lots of examples around you. I always get entertained when I look at some sort of a plume out there. I mean, it could even be the smokestack of a diesel truck or plume of a power plant. Even looking at the clouds, you can see the chaos and the formation of chaotic property changes. It's just look out there. The evidence is overwhelming. Now, let's put some more careful definitions to turbulent flows. Turbulence can be perceived as presence of eddies. Have you heard of the word eddies? Have you heard the word eddies? Where did you hear it?
For example, in mixing links in the river,
Yeah.
because of in the bed, the speed of velocity of the river tends to be static, just like the bed prevents the bed condition. But in the other depths, the velocity increases. Some eddies created there.
So you show this picture. So you drew a circle, right? So eddy, somehow we understand it as circle, and it's true. It's a local structure of fluid that spins. So this property change, when you're talking about velocity and momentum only, right, not temperature. Chaos in momentum and velocity shows itself as a spinning motion. Okay? So that we know as eddy. It doesn't have to be perfectly circle. It could be elliptic, it could be even a distorted circle, right? But it has this tendency to rotate. And you can actually conceptually show it like this. This is an eddy. Okay, so that's an eddy. And you might ask, does eddy have a size? Of course. Right? It's a structure. Any structure has a size. This building has a size. The car has a size. This pen I'm holding has a size. So does eddy. So an eddy is a structure of spinning motion. It has a size. Does it have a time scale? It does. We call this characteristic lifetime of an eddy. Why do we call it lifetime? Because eddies don't last forever. They're not like diamonds. They form and disappear, right? After some given time. So eddy has time, eddy has length, eddy also has velocity, right? How quickly is it spinning? So this could be, let's say, a big eddy. I could have a small eddy. So big eddy, small eddy. They come in various sizes and velocities and time scales. There is something that we understood from eddies by just observing the flow and making some measurements, known as the energy cascade. And this was first proposed by Louis Richardson, who's a British scientist in the early 20th century, did most of his work. He understood the concept of energy cascade, but he could not formulate it mathematically. It took couple of more decades until Kolmogorov, who was a mathematician, came and formulated the energy cascade. But let's see what is energy cascade. The energy cascade implies that turbulence, so energy cascade implies that turbulence begins with formation of large eddies due to instability that subsequently breaks down to form smaller and smaller eddies due to subsequent stabilities until they are so small that they are damped by viscous dissipation. Okay? So this is the description. So basically you have big circulating structures that break down to smaller ones, and the smaller ones break down further to smaller ones. And finally, they are so small they cannot break down further. They are dissipated by viscosity. Okay? He also had a famous poem too that says big whales have little whales that feed on their velocity. Little whales have lesser whales, and so on to viscosity. So it's very poetic. You don't speak like that nowadays. But this captures the concept. And whale here means eddies. The whale pool, right? It's a whale, right? Because in these pools, you see, there's always circulation in the water. Okay, so in fact, Richardson was a very genius person. He built the first weather forecasting model. So we can credit weather forecasting to Richardson. And he solved it by hand. It took him a long time. By the time he finished his calculation, the weather had changed already. But he put the foundations in place so we can do weather forecasting today, and now we have computers and parallel simulations, and we can do it all. But really, he is the fourth, sort of grandfather of weather forecasting research. He thought it was a dream to do forecasting someday before it actually happened. I mean, it was such a complex calculation, but he didn't know that computers would be invented in a decade or two, so they did it. Anyway, a very interesting thought. I want to make another schematic to show you this formation of eddies, basically energy cascade. I'm a very visual person. I like to have a picture for anything that I understand or want to communicate. Let's say you have a building. Here's a building. And let's say you have a wind that's approaching this building. So what's going to happen? Well, the wind hasn't approached the building yet, right? Like here it's all stagnant. The air is not moving. But the wind gradually approaches the building and starts interacting with it. One thing that happens is near the edges and surfaces of the building, eddies start to form. Okay? Now, let's say this edge of the roof can form an eddy, and in fact, this eddy will grow in size. In fact, it generates a shear layer in airflow around this building. But finally, you have an eddy that's big enough for our purposes. Okay? Well, this sounds like the reverse order of what I was just saying. I was saying big to small. I was not saying small to big. And that's still valid, right? I'm not implying any energy cascade argument here, right? This is a different, more complicated process, which we may touch on later. But I'm interested to know what happens from now on. So you have this big eddy. Now, if you watch this, it's going to break down further and further obviously this eddy is going downwind because the wind is taking everything to the right. So if you look at this eddy a few moments later, it's here, a little bit to the right, but it's broken down to 4 eddies. I mean, this is highly simplified, right? I mean, don't look out the window and expect to see this, but conceptually, this is what happens. And then further, smaller, in each one then becomes 4, another 4. And then finally, it's so small that it cannot break down further. Then the energy of chaos in the momentum, let's say the kinetic energy of this eddy, the motion of this eddy, will dissipate into viscosity. So here you can say, let's say the eddy is breaking up. Eddy breakup. Here was eddy formation. On the top was eddy formation. And then from here on, energy cascade starts. Okay, and the process goes down until the very end. You have viscous dissipation. So eddy formation of big eddies, then the energy cascade starts, eddies break up, and finally they're so small that they dissipate by viscosity. Okay, so that's the picture you can put together for the energy cascade. If you do work on turbulence, you have one of the, let's say, following few objectives. A lot of people just discover, right? They just want to discover what happens when turbulence occurs. I mean, these you could think of as a lot of scientists, right? Like atmospheric scientists, ocean scientists, people who study hurricanes, people who study oceans, even people who study space turbulence, right? The sun, for example, forms these structures every time there's a solar storm and things like that, right? So they study, they want to discover what happens. You could think of them as scientists. There's a lot of people who are in the business to model turbulence. Right? Model, what does modeling mean? Well, it means that you want to express the phenomena mathematically using logic. You have some tool. It could be mathematics. I mean, say all branches of it, right? So calculus, linear algebra, quantum mechanics. People who do modeling who express a phenomenon logically using a mathematical language. And it could be analytical modeling, theoretical modeling. It may just do it on paper. It doesn't have to be on a computer, which was done in the old days. But nowadays, a lot of modeling happens in computer world, in the computer world. So you write down the equations and then you solve them with some algorithm. So all of them are, we call as modelers. And they could be engineers, they could be scientists, depending on why they're developing this model. Maybe developing it for an application. The last group is the ones who want to control a process. And these are sort of designers or engineers, right? And they specifically study turbulence to design a process that something works better. We think of a car based on internal combustion engine. What happens in the cylinder? Air comes in, fuel comes in, and then it will mix, and they want to optimize this combustion process so the car works better. People who design wind turbines, right? I mean, why is the blade formed the way it is? Because they want to control the turbulent process so this blade works and the turbine spins and generates power. Think about the Archimedes screw, right? You want to understand turbulence in it well so you can generate the maximum amount of power and extend the life of the blade or whatever, the pump or whatever it is. So the last category is the control category. Usually are a lot of engineers who design processes. Modeling, a lot of people do, like engineers, scientists do, and they may serve a discovery process or investigation or design investigation. And discovery is pure science. So you can think of it this way. Okay, so very overall, description of turbulence. And in fact, I touched on everything here in this short chapter. I mean, the story is told, but not in detail yet. So now, it's time to actually go deep down in mathematics and the concepts, try to put numbers to things and quantify it a little bit better. Let's see if there are any questions. We have about another 25 minutes, right? Okay, good. Yeah, so let's start chapter 2 and go from there. Chapter 2 deals with equations of fluid motion. And in this chapter, I'm not going to actually talking about turbulence because I need to build the foundation of the equations of fluid motion in the first place. But it's in the following chapters, 3, 4, and 5, that I insert the ideas from turbulence. Right? So this is just, let's say, laminar fluid dynamics, equations of motion. And you have seen these in other courses, undergraduate and graduate levels. If you're undergraduate here, you might have seen your professors, Bill Van Heist, Andy Beans, teaching you this. Graduate level, you might have seen Dave Rubitz last term. You will see those. So basically, this chapter is trying to summarize all of those things in one chapter. The continuity equation. So all of physics works on a few simple principles, right? You agree with me. There is principle of conservation, and there's a principle of symmetry, right? All of physics, like any rule, law, comes from these two, right? So now I want to capitalize on the topic of concept of conservation. There are certain things in a fluid system that are conserved. The first one is the mass, okay? And this one talks about conservation of mass. In fluid dynamics, we always analyze properties or changes of properties in a given controlled space. You might think of this box as a tiny control volume in region of the space. It could be this room, it could be here, where I want to analyze property changes in the fluid. And obviously, any complex system is built from millions, if not billions, of these control volumes. If you want to study the property density, right? Density in physics, we use a symbol rho. You can actually mathematically express the change of density in this control volume. And to do that, you have to know the motion of fluid through this control volume. And this I show with symbol u, vector u, which means velocity vector. Also, this density may be of different values, right? I mean, there's no guarantee that this density is going to be conserved or constant. It may be different anywhere along this flow. So is u, right? I mean, u, velocity may change anywhere in space. But I'm interested in the change of density in this control volume. So the equation that expresses this change is the following. It's the continuity equation, where you have rate of change of density, obviously with respect to time in this control volume, plus another term, which we call advection, which we use the symbol. What is the symbol? Inverse delta or nabla. Yeah. So nabla dot rho u. So this equation is the equation for the conservation of density. Okay, and it consists of two terms: the storage term, or rate of change of density in the control volume, plus the advection. Basically, the net exchange of density at the boundaries of this control volume. Okay. Now, if you look carefully, velocity vector I've shown with a boldface. So here u is boldface. If I use a boldface in this course, that I must mean a vector quantity. Okay. But density is not a vector. It's a scalar quantity. It has no direction. It's just some number, right? So I don't use the boldface. So that's all there is. Now, here t is time, but you might think, well, isn't density constant? I mean, think of, it is already complicated to deal with if you think about density in this room of air. For all practical purposes, the density is the same, right? It's 1.2 kilogram per cubic meter. So for a lot of flow systems, density is constant. I mean, in the Archimedes screw is a fair assumption the density of water is the same, right? But if you're a combustion scientist, maybe not, right? Or if you study atmospheric flows over very long heights or altitudes, not, right? In the oceans, yes. So it depends on what you do, right? But for a lot of practical purposes, and let's say for the purpose of this course, which is a fundamental course, we can assume the density is constant. So if we assume that, the continuity equation is simplified to the kinematic condition that the velocity field should be solenoidal or divergence free. Why did I say kinematic condition? What is the difference between kinematic and dynamics?
Time.
Mass. Right? When you say dynamics, there must be a mass in there somewhere, right? F equal to ma is a dynamics equation. But when you say kinematics, you only care about motion, only velocity, acceleration, and position, displacement are there. So by canceling the density out of the continuity equation, density is not there anymore. There is only velocity. So this is a kinematic condition, right? Which is nice. In fact, how did density disappear? If you think about that, you have nabla, or divergence of rho u. But because rho u is constant, rho is constant, comes out of this divergence operation. And then you've got u. Okay? It was assumed density doesn't change with respect to time, so the first term knocked out is 0, and the second term only remains in the equation, and rho is also just a constant, you can cancel it out. So whatever remains is just the divergence of velocity vector that has to be 0. Okay? Now, you might think, okay, you didn't teach me how to take a divergence. Well, I am. The book has a rich appendix on all the mathematics you need, right? So you can go to the appendix and look up the mathematics of what is divergence, and you can look up the relationships. Okay, so even though this is not a math course, I wanted to make all of the content self-containing, which means that everything you need to know is in this book, and you just go to the appendix and look up the mathematics that you need. So same thing about numerical methods too. There is a very bit of basic numerical methods in the course that helps you understand this. So that's the continuity equation. The next equation we should discuss is the momentum equation. Let's think about it, F equal to ma. I want to teach you the F equal to ma in fluid dynamics. It's the same equation, but for fluids. So the momentum equation in fluid dynamics is based on Newton's second law, which relates the fluid particle acceleration. In other words, material derivative of the fluid velocity. This symbol we know as material or total derivative. I will explain it in detail in a bit, right? So normally we show derivative using a small d or the partial differential symbol, right? So that this symbol here. But here, this is some sort of other type of derivative with a capital D. We like to call that material derivative or the total derivative, and I'll explain this to you in detail. So Newton's second law applied to fluids will relate this total derivative. Think of it as acceleration. Total acceleration of the fluid parcel. To surface forces and body forces experienced by the fluid particle. So there are two phrases there, surface forces and body forces, right? And they both exist. I mean, even in the solid mechanics or, particle motion in sort of dynamic, classical dynamics sense. If I throw a ball up, it's subject to a body force. What is a body force on a ball on here if I throw it up? Gravitational force, right? There's some force of gravity that applies to that ball, all over the ball. Every molecule of that ball will experience the gravity, force of gravity. That's why we call it body force. It applies to all in the entire body. But if this ball hits the wall, right? Then something else happens. The surface of the ball touches the surface of the wall, and there's some force as a result of impact or touching. Well, that force is not a body force because it only applies to the skin of the ball. It doesn't apply everywhere to all the molecules, right? So it's important to distinguish the difference between surface forces and body forces. And these are what we need to develop the momentum equation, right, for fluids. Let's talk about at a very high level, about the surface force. The surface forces can be described using a stress tensor. I will tell you a little bit in a moment about what is a tensor, but see, there are different quantities, mathematically speaking, we need in physics. For example, we could have a scalar quantity, right? Like mass of something, or the time it takes for some event to occur, right? Or density. These are a scale quantity, so you have only the quantity, just one number, which gives you some property of some system, right? It could be positive or negative, right? That's okay. The sign is included in scalar. Then you have vectors. Vectors have magnitude and direction on top of just sort of quantity, right? So the vector is the next level of properties, which explains more of physics. Like, we understood for like a couple hundred years that velocity is a vector, right? Because it matters which direction you're moving to. Moving in this direction is different than moving in this direction, right? So we understood somehow that velocity is a vector quantity. Okay? Now, scalars, vectors. There's another level of definition, mathematical definition, for things that happen in nature, and that one is tensor. Think about it, tensor is like a complicated vector. It's like there are two components of direction. There are two components of direction. There's not just one component, right? So tensor is the next level of definition. And people struggle with it initially because, you know, you don't feel that every day. Same way that graduate students sometimes struggle with the concept of tensor, the same way that undergraduate students struggle with the concept of vectors, right? So in any stage of your education, there's things that sort of are fundamentally difficult to understand and grasp. Tensors is one of those, and hopefully you've been exposed to them before, but if not, then hopefully you'll get exposed to them enough, so at the end of this course, it's all no-brainer for you. Okay? And I'm going to take it to a deeper level in a moment. The fundamental property of tensors is that now you see I show tensor with symbol tau, and I put two subscripts here, I and j, right? So I'm kind of, I need two pieces of information, or two directions to define tensor. There is the component of x, which is just position, right? In physics, dynamics, kinematics, we know vector x is position. So a tensor can be a function of position, and of course time. I mean, everything changes with time in this world. So tensor, think of it as some physical quantity which depends on position and time, and you can define it for a combination of directions, I and j. I'll explain briefly. Tensors are symmetric, at least for our purposes, which means that whatever the tensor is, tau ij is the same as tau ji. So tensors are symmetric. Let us quickly now focus our attention on the body force, but then again we come back and explore tensors in detail. The body force of interest for us, I mean, for a lot of the practical flows, like environmental flows, is gravity, right? Of course, there is the body force associated with rotation, like centrifugal and so on. Like in the atmosphere, we have the Coriolis force, right? So that's also there, and you have it too. You have a body force in the Archimedes screw as well. The body force for us is gravity, and we define it in a sort of a non-conventional way for the purpose of the continuity equation. We want to define it based on the concept of potential. So suppose that the symbol psi is a gravitational potential, the potential energy per unit mass associated with gravity. The body force per unit mass, or G, can be expressed as minus gradient nabla of this gravitational potential. Okay? It's sort of a very convoluted way to put this in mathematics, but it makes things easier in a little bit. So, potential, right? Anytime you have a body force or a conservative force, the concept of potential comes up, associated. So I'm defining gravity as a function of gravitational potential. And the way I get that, I need to take the gradient of gravitational potential to get gravity. So if you like, this symbol in physics means taking the gradient of something. it's like three-dimensional differentiation. Okay, so it's three-dimensional differentiation, and in the appendix, we show you how to do it. And it will come up in the problems I'm going to do for you. So just be patient and it will show up. Like, note how carefully I defined G. I called it body force per unit mass, right? G, but G is acceleration, right, in dynamic sense. But I called it body force per unit mass. So I went from dynamics to kinematics, right? So if I normalize force by mass, I get acceleration. So I go from a dynamical quantity to a kinematic quantity, right? It's the same as saying gravitational acceleration, basically. And this is also a vector. So it's capital G, it's a vector. One of the interesting properties of gradient is if you take the gradient of something, it becomes a vector. I mean, potential is a scalar, but if you take the gradient of it, it becomes vector because you partially differentiate it with respect to x, y, and z, and then the three components give you the components of the vector. Okay, so let me say a word about tensors, or surface forces that show up in the continuity equation as stress tensors. So first of all, I want to discuss, what is a vector? Let's say, I just want to tie the concept of vectors to tensors. If you have, in physics, a vector quantity gives you direction and magnitude. And we all have worked with the Cartesian vector. Let's say if you have some velocity vector u in the x, y, z coordinate system, you could decompose it into three components. Okay, so that you would get ux, uy, and uz. And you can express the same vector using unit vectors in the Cartesian system. Unit vectors, sometimes we put a hat on them, I, j, and k, so you could express u uxi plus uyj plus uzk. So a vector in 3D space has three components, which means that you only need three pieces of information to express this vector in 3D. In 2D, it is possible, you need two components. In 4D, you need four components. So there's only one direction for the components to specify something, right? Tensors are a little bit different. You need more pieces of information. There are two senses of direction involved. Let's say if you have the same control volume of fluid that we were talking about, this control volume has actually 6 faces or planes that makes contact with the outside world. Okay, so there are actually 9 pieces of information that I need to tell me what happens at that surface as the control volume makes contact with the outside world. And I need to know all 9 pieces to be able to know what happens to the property of interest in the control volume. It could be momentum, which is at the moment, but it could be other things as well. Now, when I say tau takes INJ. INJ were the 3 components I already had, right? IJK, the 3 components, right? But tensor need the combination of 2 directions from the vector space. So I could have tau, let's say xx, tau xy, tau xz, tau yx, tau yy, tau yz. If you have 2 indices for this tensor tau, and each of those indices takes 3 options, then in total there's 9 possibilities. You see what I'm saying? So if you define a tensor over a 3D vector space, you have 9 components that express the tensors. The tensor for us, have 9 components. There's one possibility that the 2 indices are the same. You could have tau xx, tau yy, and tau zz. So these are these tensors. They're normal to the surface of interest. So that is tau zz. It's normal to the plane specified by the z vector, right? Tau xx is normal to the plane specified by the x, tau xx. And tau yy is normal to the other plane. So if these indices are the same, you get normal. So then you put the word normal. The other ones are always parallel to each surface. Tau zy, tau zx, tau yz, tau yx, tau xy, and then tau xz. So the other 6 components are tangent. And they actually specify the shear forces on this control volume. They want to slide the control volume sideways. Think about it, right? If I sort of push this top face down, I'm increasing this, right? So I'm kind of compressing it. If I pull it, I'm actually stretching the control volume, right? This sounds like a normal action on this control volume. But these other 2 are sideways. I'm trying to load the control volume sideways or put it in shear action, right? But this tensor is, it's the tau xx is not always normal. It depends on what face you're looking at. You know what I'm saying? And that's important. And that's actually why we need tensors, to understand what happens on the surface of this control volume. Resorting to vectors alone is not sufficient. You see what I'm saying? So that's why we need the concept of tensors in fluid dynamics. They help us understand what happens on the surfaces of the control volume. Now, since time is up, so I will stop here and then continue this chapter for the next class. Any questions? Thank you so much.